All right, everybody, welcome back. Today, what we're going to do is we're going to talk about vertical function transformations. All right, so to start, it's usually a little bit challenging because we see all these letters and these equations and we don't really know what a lot of it means. The one thing I want to point out is we are now using what we call function notation. Instead of having a point be x comma y and therefore an equation be something like this, instead, we now use function notation, which really means the same thing, but it's a different notation for our output values. It's not a y, it could be f of x, or honestly, g of x, or k of x, or any really letter of x. And again, it means the same thing. It's just a different notation, and that's kind of how notation works. All right, so what we're going to do today is we're going to talk about the transformations that we might see in an equation that is happening on what we call the parent function f of x. Now, a parent function is the original function. It is the function without any transformations. So in this case down here, we've got a bunch of different equations. We've got g of x, j of x, h of x, k of x are all examples of functions in function notation where there are different things that are happening to our f of x value, which again is kind of like our output value. Hopefully we did a little bit of an exploration here where we can see what happens if we graph a function, name it f of x, and then put a negative in front of it. All right, if we just simply focus on the fact that this is some output value and we now have a negative in front, well, that means g of x is really an example of f of x, except the output value is opposite. Instead of negative, it's positive. Instead of positive, it's negative. What that means is if we take a look at the graph, we're going to have what we call a vertical reflection. And now that can look like a bunch of different things. So for example, we don't know what f of x, our original function, is going to look like. It's not necessarily this one from before. It is just some generic function. What we do know is g of x is if you took f of x and you flipped it upside down. So let me give you a quick example. If this, for example, was f of x and we had a function that looked like this. Well, a vertical reflection would cause our y values to go from positive to negative and negative to positive. So therefore, in this case, g of x would look something like this. All right, where it is a vertical reflection, a reflection up and down of our original. All right, so all we want to do is we want to start to recognize what these transformations of an original function should be. And the reason we're doing that is we're kind of setting the stage for what it's going to look like later on when we talk about specific functions, such as linear functions or quadratic functions or logs or exponentials or anything like that. We are setting some ground rules that we're going to quickly be able to identify, hey, wait, this is the parent function with a vertical reflection or a vertical shift or a stretch or whatever it may be. All right, so we're trying to formulate the ground rules by using a generic function f of x. I don't know what f of x is. It is nothing at this point. What I do know is g of x is basically f of x if we were to reflect it vertically. That's what we are supposed to be getting out of an equation like this. Now, this one here is pretty similar, but there's not just a negative, there's also a 4. All right, remember, this is our output values. So essentially what we are doing is we are making our output values negative, and as we just found out, that negative means we have a vertical reflection. But then we are also multiplying by 4. All right, we're multiplying our outputs. Our outputs are like our y values, so it is a vertical transformation. So we have a vertical reflection, but then we also have, well, if you were to multiply a table of values and you multiply their outputs by 4, we call that a vertical stretch of 4. And now just to show you what that might look like, if we've got the same original function from before, f of x, and it looks something like this. All right, a vertical function just means we're going to be, or a vertical stretch, excuse me, means in this case we're going to go 4 times as high at any point. So this is k of x here. All right, instead of going up to this value, I'm going to go up 1, 2, 3 extra times as high. That means 4 times total. And we're going to end up somewhere like all the way here. Now, instead of going all the way down to here, we're still going to be 4 times its height. So really, I should make this a little bit more accurate. And we can go down to here. So now we are 4 times as high. And this and this are still 4 times the difference. So for example, this point right here is 1/4 of the height of this point. All right, and our horizontal transformations don't change. So that means the distance between here and here should be the same. But now our rounded circle here should go 4 times as high. So it's going to look something more like this. So it's probably a little bit more wide than it should be, but maybe something like this. So the idea is it's the same function, all right? It's almost the same as our original, except the difference is it's like we took it and we stretched it 4 times as high as we wanted it to go. All right, and the reason that is again, first we have a reflection. So that means when we finish this, k of x is actually going to be down here and look more like this because we have our original function that is going to be reflected, so flipped, so it should end up something like this. And then it's going to be stretched to 4 times its height, which is basically what this one is. It is our original one, flipped upside down, or vertically reflected, and then stretched by a factor of 4. So all of these rules are still going to be the same. We've got something like this, h of x. All this means is, first of all, we have multiplication in front. And as we talked about before, if you multiply your output values, it is a stretch. So this is an example of a vertical stretch of 2. But then we are also then adding a 1 at the end. Well, if multiplication is going to be stretching our values from 2, in this case, to 4, from 3 to 6, from 5 to 10, all right, adding 1 is just shifting everything up in that example. So this is what we call a vertical shift because we're shifting up 1. All right, so we're doing this so I can just quickly figure out, okay, hey, all I know here is h of x is f of x if we were to stretch it vertically by 2 and then shift everything up 1, which we're going to do in a second. Finally, our last example here, excuse me, we have multiplication in front, which is a vertical stretch of 1/3. And then now we have a minus 4 at the end. So we're just shifting everything down 4, which is a vertical shift down 4. All right, so I know it sounds kind of vague when we're talking about it like this. It's a little abstract. So why don't we look at a couple examples? So this is one where I created an f of x. That's this right here. And I've got a table of values that I use to help me plot it. Now we can talk about the domain and range of our function, which is helpful. All right, remember domain is left to right. So the furthest left I go is this point right here, which is -3. And then the furthest right I go is right here. And that's 1, 2, 3, 4, 5, 6. And I'm going to put brackets there because those are both solid points. All right, domain is left to right, or our x values, and our range is up and down, or our output values. If you notice, the lowest value in our table here is -3, and that matches. And then the highest is 6, and that also matches. All right, so now we talk about the range. Again, that is from low to high. The lowest point that I am going to go to is right here, which has a y value of 1, 2, 3, 4, -4. and then a highest point of right there, which has a y value of 2, and those are brackets, okay? So now what we want to do is I want to apply the transformations that I see right here. All right, if you notice, our outputs, remember we don't use y anymore, we're using f of x, is labeled as f of x. So g of x is going to be the exact same thing, but we don't have any f of x values, we have g of x. That's now what our function is going to be called. Well, we know g of x is really the same thing as f of x, except the outputs are going to be opposites. They're going to be reflected vertically. So my inputs, my x values, get to stay exactly the same. All right, there's no horizontal transformation, right? X's are horizontals. So those are going to stay exactly the same. Now, that means that my domain is also going to stay the same. We're only talking about vertical transformations. That means only our range and output values should be affected. So in this case, I want to multiply all of our f of x's, or our outputs, by a -1. So if I do that, I end up with +1, -2, +4, and -1. And then I can do the range as well. The range here has a low value of -2 and then a high value of +4, which is kind of the opposite of this one, which should make sense because it is a reflection. We are switching places. All right, so just to show you what that looks like graphically, I'm going to graph g of x. I've got -3, +1. I've got 0, -2. I've got 4, 4. And then I've got 6, -1. So it's going to look like this. Now, if you look at the relation between our red and our green graph, between f of x and g of x, it looks like I just reflected it up and down, vertically reflected it. And that's the whole point, because right here you're being told, hey, take your outputs and multiply by -1. That means make the negatives positives, the positives negatives, and that's what happens when you reflect. All right, so we're now going to look at one more example, and it's going to be a little bit more complicated because we're going to add in a couple of these transformations, just like the ones we talked about right here. So why don't we do this one? So we're starting off with the exact same function. I've got it graphed here. I've got my table. I've got my domain and range. It's great. All right, but here, g of x has a new value, and maybe I should name that something else. Why don't we make this p of x? All right, so I want to create my table, but we got to keep in mind all of these transformations, all of these things right here, these two things, are happening on f of x. They're happening to our output values. That means our inputs, our x's, are going to stay exactly the same. So for today, our domain is unaffected by our transformations, which should be nice, right? Now, my range is going to deal with all the work. I've got multiplication of 2. As we learned earlier, that is multiplying all of our y values by 2. So it's a vertical stretch, which I will label. And then I am adding one at the end, which is a vertical shift up 1. So we've got two transformations that I need to apply to these values. Now, everybody always asks, okay, well, which one do I do first? Well, think about order of operations. This is technically being multiplied. We have multiplication between 2 and f of x, and this is addition. Well, what happens first, multiplication or addition? Hopefully, we all know that that is going to be our multiplication. So I'm going to multiply all of these values by 2. And I get -2, 4, -8, and 2. And then I am going to shift up 1 or add 1. That is going to give me -1, 5, -7, and 3. And so again, I can do my range values from there. The lowest is -7, and then my highest is 5. And now I plot my points. So I've got -3, -1. I've got 0, 5. I've got 4, -7. And then I've got 6, 3. All right, and so what this is, it looks like if we took our red function and we stretched it twice the amount and then shifted everything up 1, which pretty much coincides with what we can see on that graph. And that should make sense because we are multiplying our outputs by 2, which is our stretch. And then we're adding 1, which is just increasing everything by 1. All right, so as you can see here, we are talking about generic function transformations. We are saying that one function is another function that is vertically stretched by 2 and shifted up 1. We know that this is happening because everything is occurring on f of x. The 2 is multiplying f of x. The +1 is adding to f of x. All of these things are happening to f of x or to our output values. Now in this case, remember, f of x isn't just our outputs, but f of x is some function somewhere that we don't really know what the equation is, but what we do know it is what we call our parent function, or the original. If you were to take away all of these transformations, you get the original function, and that's why we call it the parent. All right, so all we're doing today is we are applying different types of transformations to generic equations. A negative being multiplied by f of x is called a vertical reflection. Multiplication is a vertical, there it is, a vertical stretch. And we got to be more specific. In this case, it's a vertical stretch of 4. And then even when we have fractions that are being multiplied, we still say it's a vertical stretch. It's just a vertical stretch of or by 1/3. All right, so those ideas are the same. Finally, when we are adding or subtracting at the end, because it's again occurring to f of x, it is a vertical shift down 4. Everything we've discussed today is a vertical transformation, and the only purpose of it is to say, hey, this function, j of x, is the original, our parent function, if you were to stretch it vertically by 1/3 the amount and then shift it down 4. Again, you might say, why do I need to know this? Why is this helpful? It doesn't make any sense. A little bit later on, we will be talking about specific f of x functions where multiplication on the outside, subtraction on the outside are going to indicate vertical transformations. So we're starting with a very general formula here, things that are happening to f of x, and then later on we'll replace f of x with actual equations so we can see what that might look like, and you'll see that it will quickly help us be able to graph. Okay? So I know it was a lot. Tomorrow we will do horizontal transformations, and then we'll take some time of doing horizontal and vertical together. As always, thank you for listening, and if you have any questions, please feel free to ask.